Welcome. My name is Mike Bach, and today we're going to be talking about fracture mechanics in Workbench. This is part of our e-learning webinars that we offer. Some upcoming ones are shown up on the screen. We're going to do working with joints in ANSYS Mechanical at the beginning of August, and talk about the ANSYS Remote Solve Manager later on in August. And for additional topics, you can visit our website as shown there. Also for New Jersey and New York residents, as it says at the bottom of the screen, you can earn continuing education credits. You do have to attend this full webinar and not fall asleep. And I'll be asking a couple questions in poll format, so you have to answer those as well. They're not, it's really just to gain a little information about what you're doing out there. And then, again, we'll send a survey. And even if you're not getting credits, we'd appreciate you giving us any feedback. So let's just jump into, I'm going to start off by just giving a very brief overview of fracture. I assume many of you are well aware and probably perform this analysis. As a matter of fact, I'll ask a poll question in a second to find that out. But just to bring everybody up to speed, when you perform fracture mechanics, the real key is you're looking at and actually analyzing a flaw in your analysis. So you're basically looking at a crack of a given length and at a certain position and location in your model. You're using materials where you know what the fracture toughness of that material is, and you're trying to predict if that crack will propagate to fracture. So the key thing in fracture mechanics is you're actually looking at a flaw. It's not a smeared out kind of thing. It's an actual flaw. And as an example, just real quick of why you'd want to do this, something I worked on, there was a wind turbine failure that we were called in to look at. And there were a number of wind turbines. One had failed, so they shut all of them down. And the question brought to us was, can we start the other ones up, and how long will they last, and what should we do? So after inspecting and seeing how the failure occurred, we then had all the other non-failed ones inspected to see what type of cracking was occurring in these shafts. And knowing what the size of the flaws and the current cracking and knowing what the loading is, we could use fracture mechanics analyses to determine, based on the given flaws that we could see in the existing ones, we could predict how long until those cracks would propagate. And then at that point, you can then, using safety factors and so on, you can set inspection intervals to say, okay, you can turn these other ones back on, you can run for another 10 months, and then we recommend you inspect again, and then you redo the analyses and so on. And that's kind of the idea of how fracture mechanics would get used. So as a starting point, I'd like to have Christina give you the first poll question. And there it is on the screen. And basically, I'm just looking to find out for any of you who are attending if you currently perform any kind of fracture analysis with or without, ANSYS. I'm just looking into kind of what level the audience is at. So obviously your choices there are you do it all the time, you're an expert, and you should actually be giving this webinar, or you never have, but you're kind of interested, or you don't really have a need, but it's too hot to go outside at lunch, so you just thought this would be a much more interesting way to spend your lunch hour. So, or if you're not sure, there's always those people that really aren't sure of anything. So please select your choice, and then we'll the answers came up here, and as has been the case when I've done this, about around a third are doing this analysis, and another third are interested, and the other third aren't sure, and that's pretty close. So that's kind of what I expected, and that's good to know. I'm glad to see people are out there doing this kind of analysis. So thank you for chiming in there. Okay, so what I'd like to do, I'm going to spend the next few minutes just going over a little more detail, and then we're going to jump in and I'll show you some of the new features that are available in Workbench. First thing is fracture mechanics. As I said, we're modeling the crack actually in the structure, and the stresses near the tip of a crack in an isotropic material, that can be derived from theory of elasticity. These are not things that are estimated or correlated with testing or anything. These equations can actually be derived. And the key thing to note is that R is the distance from the tip of the crack. Notice that the stress expressions all have 1 over the square root of R term in them, which means as R goes to 0 and you approach the tip of the crack, the stresses are going to infinity. And in linear elastic fracture mechanics, that's the key, is we're saying that, okay, we're accepting the fact that the theory of elasticity says the stress goes to infinity, which isn't going to help us. If you do a stress analysis, we can predict infinity, and that doesn't really help us. But what these equations do is there is this factor K1, and you can also, by the way, derive K2 and K3, and that is your stress intensity factor. That is a function of the crack geometry and the applied loading, and that stress intensity factor is the key in linear elastic fracture mechanics. We can compare that to the fracture toughness of the material to determine if the crack will propagate. So we're accepting the fact that the stresses are infinite at the crack tip, but we're using the derived expressions to calculate this stress intensity factor. Notice that there are 3 different modes, and you can calculate 3 different stress intensity factors at a crack tip. Mode 1 is typically the one most people are interested in. It's where you pull the thing apart, a tensile mode crack. There is mode 2 sliding and mode 3 kind of the tearing out of plane. You can do mixed mode fracture. A lot of fracture people will claim that if you're doing like crack propagation, the crack always tends to kind of want to end up in mode 1, so it'll take a path such that it'll end up being mostly mode 1 anyhow. That's why we look at it, but there's a lot of mixed mode fracture analysis being done as well. ANSYS Mechanical, and of course this is available in APDL as well, allows you to calculate the stress intensity factor directly, or you can obtain the J integral or the energy release rate using the virtual crack closure technique. These are now all available both in Workbench, like I said, and Mechanical APDL. As you can see, for a linear elastic material, J, G, and K are all related, so you can decide which technique you'd like to use, and then you can relate them back. There are many reasons why you might want to choose one versus the other. The J integral, for example, can handle when you have plasticity at the crack tip that you're modeling. The energy release rate is used many times for delamination problems, so there's different reasons why you might want to use the different techniques. Let's talk about fracture toughness real quick. Fracture toughness is a material property, so it's just like the modulus or Poisson's ratio or density or anything else. It's a measured material property of a material, and it is usually found through different standard specimen. A compact specimen shown below is an example of one, and the way it works is simply for a simple static fracture is that you can put your crack in the model, calculate the stress intensity factor, and then compare it to the fracture toughness. If the stress intensity factor for that crack and that loading is greater than the fracture toughness, then the crack will propagate. If it is less, the crack won't. Now, what's really of more use is when we combine fracture with fatigue. A lot of times we have cyclic loading For example, the wind turbine problem I mentioned. In that case, you have a cyclic loading as this thing is spinning, and therefore you can combine fracture with fatigue so that you can calculate how much the crack will propagate for each cycle of loading, and then you can predict at the end how many cycles to failure. We'll talk about that. That's a topic for a different day, so we won't talk about that today. Today we're just talking about how to calculate the stress intensity factor for a given load. And we'll have to schedule a fracture and fatigue e-learning if there's interest. Okay, so there's essentially two ways to approach this, and then I'm going to basically show you the second way. The first, but just to be clear, when we do these types of analyses, one way that people do this is where they won't include the crack in their finite element analysis. They'll just run the finite element analysis to get the overall stress field for their particular geometry and loading. And then they'll take the local stress field at the region where a crack has either been inspected or is expected to be found, and they'll take those stresses and put those into a standalone fracture code. Some examples are that NASGRO is one, AFGRO. ENCODE also has, which is in the family of the ANSYS programs. ENCODE, which is a fatigue program, also has a module that will do this as well. But essentially, these codes have libraries of standard different crack types, like a center cracked plate under tension load, or an edge crack, or different 3D cracks. They have a library of solutions for K1 and stress intensity factors. So what you do is use your finite element analysis to grab the stress in that region, and then you push those stresses into these codes and then calculate what the stress intensity factors would be. Or the more difficult way is if you build the crack directly in your finite element model and then calculate the stress intensity factor. And that's what we're going to talk about today, because that's some of the new features that are in Workbench. Keep in mind, it's a challenge to do this. There's a couple reasons. One is, if you're modeling a crack, the crack will affect how the load gets redistributed around that crack. So you won't get that effect using the first method. When you actually put the crack in your model, the load is automatically redistributed so that you get that effect. But the problem is, we don't always know exactly where the crack's going to, if you want to start modeling the crack propagating, if you don't always know ahead of time where the crack's going to go, and you're going to have to try to have reasons to or techniques to figure out which way the crack's going. So it's not a trivial thing to put a crack in a model, and it's not trivial, as we say here, just to put a crack in a model, just to put, even if you know where the crack is, to model it is not trivial. So just because you have to split the geometry and you're going to have to change the mesh and do stuff at the crack tip and so on. So what I'm going to show you today is Workbench in 14.5 in mechanical provides a couple of options that allow you to put a crack in your mesh. And the two methods are either coming in already with your geometry or mesh already with a crack in it, and you're just going to identify it in Workbench and tell mechanical, look, this is where the crack is, use this crack and let's calculate K1. Or you can come in 3 dimensions. You can come in and say, I just want to crack at this location, and it'll automatically change your model to include that crack. We're going to show examples of both, or I will show examples of both right now. And the final thing I wanted to point out is that a lot of especially the automated crack creation, a lot of the inputs, like the crack size and location and mesh density and so on, can all be assigned as parameters in Workbench. So if you've attended our previous e-learning on the parameter manager, there's a lot of parameters, and I'll identify them in my as I go now to start doing the demos. I'll identify that you can create parameters so that you can run a whole bunch of different cracks automatically without having to do everything manually. So I'm going to switch now, and I'm going to show two different demos. The first one is going to be a pre-meshed crack. That means you've built your geometry such that the geometry contains a crack in it. And you can do this in 2D or 3D. So if you've already created geometry, or if you already have a mesh, you can bring it in through FE Modeler and then just say, okay, you're going to identify where that crack is. And so that's what I'm going to do. And just to make this fairly easy, I'm going to do a 2D model, just for time's sake. So I brought in this 2D model, and what I would like to do is basically running. It's a plate with a center crack, and I have a symmetry plane up here, so I'm only running the right-hand side of the crack, and I want the crack to run from the center to the center of that concentric circles that you see there, right to the center here. And I purposely made these cuts in Design Modeler just because I want to make sure I have a nice mesh around the end. Now, ANSYS uses contour integration to perform all of these the calculations. So the contour integration doesn't require, but it'll be much more accurate if you have concentric kind of circles of elements emanating out from the crack tip. So I just automatically did that. And the way it works is my geometry, the top and the bottom are currently unselected. I didn't want the code, I don't want this to be continuous because I want a crack at this region right here. And I also don't want to put contact in there because that'll kind of glue everything together. So I left the top and the bottom regions totally separate, so they're unconnected at this point. Under connections, notice under generate automatic connection on refresh, I set it to no, so it wouldn't automatically create contact. And what we're going to do is I'm going to create mesh connections to connect these together. And I don't know if any of you are familiar, but I thought this is one item that you might be interested in, is you right-click on connection and say Insert. Instead of manual contact regions, you can do manual mesh connection. And a manual mesh connection, basically I can select, if we switch to lines, I can select this. There's two lines right on top of one another, and I want to make sure the mesh is continuous across this boundary. So I'm going to select using the plane select. I'll select the top one and make that the master, and I'll select the lines again there and use the plane select to select the lower one and make that the slave geometry. What I've done now is I've created a mesh connection that will create a continuous mesh across that boundary. So this isn't modeling contact here. We're actually forcing the code when it goes to mesh to create a mesh, a continuous mesh across that boundary. I have to do the same thing here because, again, the crack is going to go from the center symmetry line to the center of that hole. So these other two regions, I got to do the same thing. So I'm going to right-click, insert a new manual mesh connection, and I'm going to pick that line, pick the top one, and apply it. And again, pick that line, pick the one underneath, and make that the slave. And now I have a second mesh connection, and I'm going to do one more, zoom in, and I'm going to use this line, the top one, for the master, and pick the same thing except pick the line underneath it. And now I have three mesh connections so that it will create a continuous mesh across there. Now, at the front, on the front three lines, they will not. So that will be where the crack is. They're going to be unconnected. Okay, so to start getting ready to do the crack, one thing I have to remember to do is I have to create a coordinate system for my crack. And the coordinate system has to be in where the crack, on the open side of the crack, with X pointing towards the crack tip, Y perpendicular to the crack surface. So if I go into coordinate systems, I am going to insert a new coordinate system, and for convenience, I'm just going to use one of the vertices that lies right in front of the crack, and I'm going to say apply. And it just so happens in my model that X is already pointing towards the crack tip, Y is perpendicular, because the crack, think of the crack as going into the plane in my 2D model, so Y is perpendicular to the crack face, and Z is pointing along the width of the crack. That's exactly how I want it to be. I'm going to change the name of that, rename it to crack CSYS for my crack coordinate system. And now I have some mesh settings to make sure I get a fine mesh at the crack tip. So I'm just going to generate the mesh. It only takes a second to generate. And because I did my mesh connections, it will create a continuous mesh behind the crack tip, and then it won't connect the mesh where my crack is located. And that's exactly what, as you can see along the back side here, the crack, the mesh perfectly lines up and it's connected. And in the front, it won't be. Okay. I have to, one other thing you need to do before we do the crack is when you come in with a pre-mesh crack, you have to tell ANSYS, you have to create a name selection of the nodes that are on the crack tip. So we have to create a nodal name selection at the crack tip, which is right at that point there. So the way I'm going to do this is I'm going to select a vertex, the vertex at the crack tip, and I am, make sure I got that okay, and then I'm going to right-click and say Create Name Selection. And it's going to create a name selection. I'm going to call this Crack Vertex. Click OK, and now it's slow, but it'll get there. Eventually, it will show up under my name selections that I have a name selection. Again, because it's 2D, my crack front is just one vertex. There's not multiple ones there. So now I need to get, that's the vertice. I need to get the node. So there's a way, if you right-click on that, to say Create a Nodal Name Selection. And what it does, it creates a nodal name selection. If you click on it, you'll see it'll bring up the worksheet and show you that it grabbed that vertex and then it converted it to a mesh node. So that represents the node that's on that vertice. So I'm simply going to rename it as Crack Node. And so now I have a name selection at that location. So at this point, you can either enter under Model and insert fracture. We already did that, so the fracture tree structure is already there. So I'm now going to right-click on fracture and insert. You have two choices, a pre-mesh crack or you want to create a crack. This is a pre-mesh crack. We brought the crack in with our model. So I'm going to use pre-mesh crack, and down at the bottom, it wants to know where's the crack tip. It wants a name selection. I give it the crack node, so that tells it where the crack tip is. Then it wants a coordinate system because it wants to know how that crack is oriented. So I will change that to the crack coordinate system. So now it knows the crack tip. It knows how it's oriented. It now says, I understand that you have a crack in here, so now I will go ahead and run this analysis. I have some loads on here that are pulling it in tension. For time's sake, I have the solution here. And what you see, once we run this solution and we have again, we were just pulling on this as a tensile load. You can see the crack opening up. It's pretty clear that the mesh here was continuous and the mesh out front was not, and therefore I have a crack. If I look at the equivalent stress, you see what many people call like kind of a kidney bean shaped stress field out front of the crack. And if you zoom in, you do get a value of stress that's not infinite because we're doing a numerical procedure. You're not going to get an infinite stress. But that stress is a function, obviously, of the mesh density. The finer you would make that mesh, the higher the stress would go. It's not really telling you much. What we really are interested in is what is the stress intensity factor. So what you would do is under solution, you insert a fracture tool, and that would appear here. And then under the fracture tool, you can say insert, and you have the option to do J-integral, the stress intensity factor 1, 2, or 3, or you could use VCCT and get the G values. In this case, we know that we're pulling this to opening mode, so we're interested in K1. So you get K1, and again, what it does is it's basically automatically finding element lanes that it's going around in contour. So if you look at the mesh, it's essentially doing contour integrations as it goes around, going outward and outward for each contour. And you can set the number of contours that you'd like under the fracture here, solution contour 6. You can pick as many contours as you want. For most simple problems like this, if you look at the results for the different contours, there's usually error in the first one, but as you start moving outward, you should see that eventually they kind of converge to a solution. So by the sixth one, for this particular case, we have a value of 0.0746, which also shows up in the details. And now you can compare this value to the material fracture toughness to determine if this crack would propagate. And that's kind of the general procedure. That's sort of interesting, but it's only 2D, and we had to come in with our crack geometry. By the way, you could have come in with a crack mesh as well if you built something in APDL, and you could bring through FE Modeler, you could bring in the whole mesh already with a crack in there in your complex 2D or 3D geometry. You could do that as well. Again, you would just have to add the fracture part, tell you have a pre-mesh crack, assign the coordinate system and the name selections, and you're good to go. But let's say in a more general case, we're interested in a 3D model that we built in Workbench, and we don't have a crack built in. So let's say we want to put a crack down in this fillet region here. Well, right now there is no crack, and we didn't bring it in the geometry or the mesh. So in that case, we can use the automated crack operation. Now, to do that, the first thing we need to do is create, again, a coordinate system that will identify where the crack is going to appear. So what I've done on this particular model is in this location there is a vertex that is where I want to put the crack at. You don't need to use a vertex here. You can you can just find out where the coordinate is as coordinate location in space, or any other way to do it. In this case, I knew where I wanted to model the flaw, and I just, in the geometry, built a vertex right at that location. And so now I'm going to go in to the coordinate system and say insert coordinate system, and I'm going to say under geometry selection, I'm going to apply, and it already knew that, we're going to apply it at that vertex right there. So it sees where that origin is. Now the thing is, when I create that, it's going to create the coordinate system by default so that it lines up with my global. So the global X is lined up with the X. But we want the X-axis to be pointed towards the crack. So, and here's one of the limitations of Workbench right now is in a 3D model, a crack has to be perpendicular to the surface. So we have to create a coordinate system that the X is pointing inward and perpendicular to the surface. Well, there's a way to do that, by the way. Down here in the details, I can say point the X-axis not to the global, but do it based on a hit point normal. The hit point normal is going to say that it's going to find out and calculate the normal, and it's going to redirect the X-axis in that direction. So I change it to hit point normal. I click the change. I click apply. And sometimes it doesn't always work the first time. You got to click it again because it's hot out, so it's just lethargic. So, but there, what you see now is it the X is now pointing inward, if you can kind of see that. X is pointing normal at that location into the surface. Y is going to be perpendicular to the crack face, and Z is going to be along the other direction of the crack. Now, here's another situation or limitation right now in Workbench 14.5. You can only model a semi-elliptical crack on one body and in one surface. So the crack can't cross surfaces, and it has to be contained fully in one body. Again, that's not a big deal because in most 3D models, we can, that's what we're looking for. By the way, a semi-elliptical crack, you can think about it as if you stuck your fingernail and indented, if you were like Superman, if this was steel or something, and you stick your fingernail in there, that would create like a semi-elliptical crack. So that's what we're limited to. Right now, you can't do a corner crack. It has to be a full elliptical crack. I'm sure a lot of these limitations will go away. Okay, so you'll notice that we already have a mesh in our model, so we're going to have to insert the information for our crack and then tell it to remesh this local region. So let's do that. Under Model, I right-click, Insert Fracture, and then under Fracture, I right-click, Insert, and now I'm just going to say Crack. I want to have the automatic creation, not a pre-mesh, because I haven't pre-defined the crack. I'm creating it automatically here. So we have to fill out a few things down in details here. The first one is, what is the geometry? Well, I'm just going to pick this full body. I only have one body, so I scoped it to that. The next thing is the global coordinate system. No, I don't want that. I want, as a matter of fact, let me rename this, the one I created, to crack CSIS again, just so if I come back to this, I'll know. So if I go back to my crack here, under the coordinate system, let's change it to the crack coordinate system that's normal to the surface that we created. Notice the crack shape is fixed, semi-elliptical for now. Major radius, I just have some numbers I can put in here. So I'm going to put in 0.0184, and the minor radius is 0.0095. You'll notice if I can zoom in here, you'll see that it automatically shows you what that crack looks like. So there you see the semi-elliptical location and the size based on what I just entered. Largest contour radius, I need to put something in there. That's talking about the mesh. Notice that we're going to create this contour radius here. So it's basically talking about what the radius of this circular mesh that's going to go along the crack front. So again, you have control over a lot of the mesh because it's so important to get a good mesh of your crack tip. So I gave it the radius of how I want that. How many do I want circumferentially in my mesh? I'm going to put 16 in there. And how many crack front divisions do I want along? So notice it changed the mesh looking there, so it had 16 elements going around there. And then the crack front, we're going to say 35. And notice that along the crack front, it's going to give me 35 elements along there. And you can notice that all these inputs have the little box there saying that you can click those and make it a parameter so you can change whatever you want. At this point, there's other things you can do, but for time's sake, we need to right-click and say Generate All Crack Meshes. So now we're going to go ahead and do that. If you notice before when I was doing this, not only did it show a crack mesh, but or where the crack was located, it was also showing a nearby block. That's called the transition region, and essentially the code is going to use the mesh from far away, and it'll mesh what you want right at the crack tip, crack front, but in between that, it uses a transition zone to hook the global mesh up with your crack mesh. That's another limitation. Right now, the region where you're going to put the crack in 3D has to be made of tetrahedron so that it can perform this transitioning. So make sure the region you want to put the crack in is made of tetrahedron. So what you can see at this point is it now created the crack front mesh. Notice that this is unconnected along here. That's a crack that goes into the model, and it did the transition as we asked it to. And if I zoom out, you can see, it did. You can see where the crack mesh is located, and at this point, you would put on your boundary conditions and load this. In this case, this model, I have a tension load on this and symmetry boundary conditions elsewhere. So again, since we're already a little bit over time, let's go right to the results that I already solved. And what you see, the first thing you see is if I look into the results, you can see if I plot the total deformation, there is, you kind of see that, I guess, is that's the elliptical crack kind of opening right there. So you can already see that the crack wants to open because we're performing a tension load there. And then again, same thing. You would insert a fracture tool, and then you would insert what results you want to see. Again, since this is an opening crack, and for a short period of time, we plot the K1, and now we're going to get K1 all along the crack front because this is 3D. If I zoom in a little bit and kind of rearrange this, you can see that it puts a little contour along there showing from point 1 over to point 2, and then down here in the graph, it'll graph for each contour. Remember, as it goes out in the mesh, it's taking contours going around. In each contour, it's plotting them. And again, as usual, the first contours has some error, but as you go to the following contours, it pretty much converges. And you can also, over here for each contour, get the value of K1 as you go around that crack tip. And in the details, you will get the minimum and maximum for whatever in this case, it's the last contour. You're getting the min and max value. And again, you can then start comparing this to see if the crack will propagate based on the fracture toughness. There's a lot more you can do. I simply wanted to at least try to quickly demo this. And like I said, we've already gone over time, so fortunately can't really show too much more here.